It's very nice to have Abhishek back to talk about hardness of approximation for the most matching problem. So Abhishek is finished his masters now at Munich and is doing his PhD there. So he has for a long time worked on various problems in math and computer science, and has always been involved with topology and computational topology from the age of six. And he continues to do that for his PhD. So looking forward to this.
Thanks a lot for the introduction, and thanks also for inviting me to give a talk. So today I'll talk about hardness of approximation for most matching problems. The meaning of this title will be clear in the next few slides. Like Rajan just said, my name is Abhishek, and I am currently doing my PhD at Technical University of Munich. So this talk is based on the paper that was accepted to SODA 2019, and I have pretty much not changed the slides, but I'll be going a lot slower than what I did there. So I'll start with the introduction. Let me begin with classical Morse theory, just to recap. So in classical Morse theory, what you do is you consider, you have a geometric object like a manifold, and you have a function defined on it. It's called a Morse function. And what you do is you look at the sublevel sets of a function on a manifold, and you track changes in topology as you go across sublevel sets. So for instance, the sublevel set at function value c, let's call it fc, is basically the part of the manifold which has function value less than or equal to c. So for instance, if you have a c, then this part is the sublevel set. So as you can see, if you look at the sublevel set of C minus epsilon, so it's this thing it looks like a disk, and which you can shrink to a point. So it has the topology of that. It's homotopy equivalent to a point. Whereas this one is the C plus epsilon sublevel set is a cylinder. So it has the homotopy type of a circle, and the change happens exactly at the critical point, which is C. So here, at point C, you have a saddle. So this is in fact the punchline, let's say, of classical Morse theory, that the topology at a sublevel set Fc changes exactly at the critical value of F. And when you study changes across all the sublevel sets, then this gives you the full description of the homotopy type of a manifold. So interestingly, there is a very good discrete analog of classical Morse theory. It's called discrete Morse theory, and I mean it's applicable to cell complexes, but to regular cell complexes. But for the purposes of this talk, we'll stick to only simplicial complexes. And discrete Morse theory is actively studied in algebraic, geometric, and topological combinatorics. So it's quite relevant in pure mathematics, whereas it's also a popular tool in topological data analysis and visualization communities. So in Professor Natarajan's lab, you'll see a lot of work that was done, especially by Nitin, on discrete Morse theory in this applied context. So let me start with the basics of discrete Morse theory. Now, the definition here is not the one that you'll find in Robin Foreman's original papers. This is a slightly modified version of the definition, but it's equivalent. So it's just more elegant and easy to use. So a function f on a complex k is a discrete Morse function if two conditions are satisfied. Number one, f is monotonic, which means that if sigma is a phase of tau, then the function value at sigma is less than or equal to the function value at tau. So for instance, if you see, let's say this one, this edge. So the function value is 6, and it is a face of this triangle, and the function value of that is also 6. So this is satisfied. Let's say you have this edge here. The function value is I don't know, 1, I think. or no, 4. 4. Function value is 4, and the function value here is 6, so it's satisfied. And this is true for all the simplices for this example. The second condition that is satisfied is that for all t in the range of f, the inverse image, the pre-image, is either a singleton, in which case it's a critical simplex, or it's a pair, such that one is a facet of the other, in which case you say it's a gradient pair of regular simplices. So, for instance, if you take the pre-image, so for this complex and this function on this complex, the range is 1, 2, 3, 4, 5, 6. So if you take the pre-image of 6, you get 6 and 6, and such as one is the facet of the other, so they form a gradient pair. And if you take the pre-image of 3, then you just get this edge, and it's a critical simplex. So, so you can check easily that for this example, these two conditions are always satisfied. So, oh, sorry, yeah, you're right. Yeah, sorry. So it's 5. In this case, 5 is the critical simplex, and 3 is this is a pair. Yeah.
So this definition, we started by talking about defining function on a complex.
Yes.
But you focus only on Euclidean complexes, or this is something that intended for regular?
This works for regular complexes also. So I think this probably appears first in Kozlov's work. This variation, but I think Bauer uses it for Uli Bauer uses it for almost all his discrete Morse theory papers. And from that's where I got it. And I think it's also called like flat discrete written Morse function or something like that in Foreman's papers. But it just so happens that this the real object of interest here is the gradient vector field, and this has all the gradient vector fields which the original, where you also allow in that the original definition, you also, if sigma is a face of tau, then f of sigma can also be greater than f of tau. Here it's not possible. So here you are either equal, in which case it's a gradient pair, or you're lower. So that's like the main difference. But yeah, over there you allow for at most one higher, and here you don't allow any higher. You have them either equal or you have them smaller. When it's equal, then it's a pair. So that is the difference. So because of that, you can nicely formulate it as like an inverse image and the other monotonic. Otherwise, the original definition, you do not even have the monotonicity. Now you have this monotonicity and this other property as well. And once you have that, once your simplices are, once all your pre-images are either critical simplices or gradient pairs, then you look at all the gradient pairs. You look at the collection of all the gradient pairs, and this collection of gradient pairs essentially gives you what's called as the discrete gradient vector field associated to the function f. So, so this is all you really need to know about discrete Morse theory, more or less, to understand this talk.
But is this really an equivalent to that other definition, or this is stricter?
Well, yeah, I mean, maybe equivalent is not the right word. Okay, so I would say that for every gradient vector field here, there's a gradient vector field here, and for every gradient vector field here, there's a gradient vector field there. It's just that you may have, in terms of function values, it's restrictive, but in terms of gradient vector fields, it's you have the same here and there. So yeah, it is restrictive in terms of function values. So I will now define the problems that we're looking at. But just before that, I'll talk about one main prior work, which is by Josvik and Fesch. So they basically proved in 2004 that if you're given a simplicial complex, now as you can see, the construct of a gradient vector field is entirely combinatorial. So is the definition of a simplicial complex. So you can talk about, you can ask classical complexity kind of questions about what is the optimal gradient vector field. When I say optimal here, I mean what is the gradient vector field? So of all possible gradient vector fields that you can have on the complex, which are the ones which have minimum number of critical simplices. So any such gradient vector field which has the minimum number of critical simplices is an optimal gradient vector field. Computing such an optimal gradient field is NP-hard. And they posed in 2004. They proposed so it's kind of they pose the approximability as well as the inapproximability as an open question, but they do it in a looser language. So in the sense that it's like it's not clear what they are saying, which of the problems they are calling open, but I just assumed that everything is open, and it was open. So when you talk about optimality, you have these two variants, and the two variants are the same. So you can say I want to compute a gradient vector field with minimum number of critical simplices, or you can say that I want to compute a gradient vector field with maximum number of regular simplices. And when you talk about optimality, so the optimal gradient vector field will also have the minimum number of gradient vector critical simplices, and will also have the same number of regular simplices. But from point of view of approximability, these problems are different in the sense that you have the optimal value here for minimum, and you want to compute a fraction of or some multiple of the minimum, and trying to approximate this problem is different from trying to approximate the problem where you have a certain number of regular simplices, and you can your approximately optimal is a fraction of the total of the optimal. So these, from the point of view of approximability, these problems are very different in nature. From point of view of optimality, they are the same. So the results are the following. You have for minimum Morse matching, we have the following result. For complexes of dimension d greater than or equal to 3, assuming p not equal to np, basically there exists no O of n to the 1 minus epsilon factor approximation algorithm for min Morse matching. So this means for minimization problem, this is actually quite bad. So, but for maximization, you cannot. We were not able to prove something very strong. What we were able to prove is it's NP-hard to approximate max Morse matching with a factor better than 1 minus 1 over 4. So basically 4913 over 4914, and UGC hard to approximate it with a factor better than 701 over 702. So these results are not that strong, and that one is like quite strong. You cannot. It's like this. This says that it's quite hopeless to try to minimize approximate the minimization variant of the problem, but this says that the other one result says that it's not that hopeless to try to approximate the maximization variant. So in fact, actually, I'll go back to the previous slide. But so this is the joint work with Professor Natarajan here, and this was we proved approximation algorithm. We showed some approximation algorithms for max Morse matching in the CGTA paper in 2017, and other related work being so there's a long line of heuristics for trying to compute the optimal Morse matchings. I will not list them here. And for parameterized complexity, Burton et al. Showed WP hardness in 2013. Yeah, so one reason why trying to compute optimal or near optimal gradient vector fields is the following. So many times you want to do topological computations, and you have a large complex K, and it would be very useful if you have a fast way to transform this large complex K to a smaller complex K prime, such that the two have the same topology. And if you can do this fast, then you would rather do your topological computations on the smaller complex instead of the larger one. And it turns out that discrete Morse theory is one way to do this. And this is because of the following theorem by Foreman. So you start with a simplicial complex with n simplices, and let V be a gradient vector field on K with m critical simplices. Then K is homotopy equivalent to K prime, and K prime has only m critical simplices. So you may start with a simplicial complex with K simplices, and you will end up with a much smaller cell complex with K prime with m cells. And if you're lucky, you can this is fast, and also m is very small compared to n. But it's like because it's like hard to approximate, you will many times not have this, but when you have, it's very good.
So this one maybe does not satisfy the regularity condition, right? The cell complex A prime
Um,
be regular.
no, it need not. It need not
So
be
is
regular.
there something which say what is the non-regular complex?
Oh, mm, I mean, I think what you can do. I have to think about this, but
This is like your handle body
yes, 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 yes,
configuration, right?
yes, yes, yes. So one thing that you can do though, even if it's not regular, you can keep so the faces that are on which there is just uh, unique incidence from those faces you can keep reducing. So you can so there's a way to do that, and you can. So I think this comes up in algebraic Morse theory, where you have, so if the incidence is just unique incidence, so on those faces, so some faces will be multiple incidences and those you cannot touch, but the unique incidence one you can continue to reduce. But I have to think more carefully about what would be the minimum regular cell complex. Maybe there's a good answer also to that. So okay, so so in the so the minimization proof for in approximability is not very difficult. It's just one page and it's not very difficult to read. So I'll just focus on the maximization variant for this talk, because here there are some maybe new ideas and it's somewhat interesting. So the reduction is from some. So basically, these kind of hardness results are often obtained from reduction from other NP-hard problems that are known in the literature. You also know they are what is the hardness of approximation results already known through literature for these problems, and then you do the reductions. So so we look at the following NP-hard problems on directed graphs. One is max acyclic subgraph. So you are basically given a directed graph, and you want to find a maximal subset of edges that induces an acyclic subgraph. So if you look at the graph there, the blue edges in that graph is one such maximal subset of edges that induces an acyclic subgraph. Now we are in particular, so we are using the so-called L reduction, which is a unique type of reduction, and to have that property, instead of doing the reduction from max acyclic subgraph, we do the reduction from a restriction of max acyclic subgraph to oriented simple directed graphs that have degree 3. By this I mean, by oriented I mean that you don't have parallel edges. And by degree 3 graphs, I mean that the in degree plus out degree is less than or equal to 3 at every vertex. So we will be doing the reduction from this problem, 3 mass. The complementary problem for max acyclic subgraph is min feedback arc set, which comes up in one of the corollaries. It's not the problem which we'll reduce from. So this problem is that you are given a graph and you want to find the minimal subset of edges such that when you remove these edges, what is left behind is acyclic. So for this example, the red edge is the edge which constitutes the minimal feedback arc set. So these two are complementary problems basically. So the reduction strategy is following. You have what you do is you transform instances of 3 OMAs, which are directed graphs, to instances of max Morse matching, which are simplicial complexes. So this is a function k, so or you can call it a complex kg. So you go from g to kg, and you also need another transformation from solutions of max Morse matching. Let's call them. So you have kg and you have vkg. So gradient vector fields on kg. From there you have to go to acyclic subgraphs that are obtained from this gradient vector field. And these acyclic subgraphs, these are subgraphs of G that are acyclic. So you go from instances of mass, which are directed graphs, to instances of max-most matching, which are simplicial complexes. These are Kg. And then you go from solutions on Kg, which are VKG, which are gradient vector fields, and you go back to acyclic subgraphs. So any questions about this? So this is basically the reduction strategy. The acyclic subgraphs? No. So note that you are doing. So these are not necessarily the optimal gradient vector field. So you are saying that you have a function which transforms every gradient vector field to an acyclic subgraph. Okay, so which is why, I mean, even if it was just the optimal, even then you may have many optimas. So, but we are not even talking about that. We are saying that transform all solutions here to solutions here. So instances from here to instances there, and solutions from, so this is reverse. So instances from here to here, solutions from there to here. So so before we look at the actual reduction, we need a building block. So this is done. The reduction is the hardness proof uses a gadget, and I'll first describe the gadget and introduce some terminology. So some definitions for that. So you have you say that complex is collapsible when. So this is not really the definition you'll find in literature, but I've couched all in the discrete Morse theory language so that it's consistent for this talk. So you say that a complex is a collapsible complex if an optimal gradient vector field on this complex has a unique critical simplex, which will be a vertex. So when a complex has such a gradient vector field, such an optimal gradient vector field, which has a unique critical simplex, then you say that the complex is collapsible. And a simplex, you call a simplex a free face if it has a unique proper coface. Okay. So for instance, if you look at this edge Lj, it has a unique proper coface Lgj. So Lj is a free face. Whereas this one is not, because it has two cofaces. Now, a simplicial complex that is collapsible, and so this is so now let's look at this example. So this is like a triangulated cone. So you take, so the color coding here says identification, indicates identification. So you identify this edge to this edge, this edge to this edge, and this edge to this edge. So you start with the triangle and you just make a cone out of it. And on the base of the cone you have free faces, and everywhere all the other edges are not free. So and the figure here shows an optimal gradient vector field on this particular complex. And as you can see, that has a unique critical simplex, which is A. What we really want for a gadget is something different. I mean, we want a collapsible complex, but we want a collapsible complex with a unique free face. So this is maybe very close to what we want, because it has 3, but we are looking for something that has just 1. So we will first look at this very famous complex called dunce hat, and then we'll try to modify this dunce hat so that it has just 1. But the dunce hat is a complex where first what you do is you do exactly what you did before. You identify this edge to this edge as indicated by the colors. So you first make a cone out of this, and once you make a cone out of this, you identify this purple to this. So these two purple will already be identified, and that will be identified to this, the blue to this, and the green to this. So you first make a cone, and then you identify this edge of the cone to the base of the cone. So it's hard to visualize because it's in it doesn't embed in R3. So this complex is a complex that is contractible, but not collapsible, and it has no free faces. So it's not collapsible because optimal gradient vector field has 1, 2, 3. Yeah. So how many are they? Oh, so 1, 2, and 3. 3 gradient critical simplices, and yeah, and it has no free pieces because all the ones on the sides are also identified. There's nothing that's not identified to something. Again, so what's desired here is a collapsible complex with a unique free face. So we'll try to modify this to make that happen. So this is the so-called modified dunce set. So if you can see here, the only simplex that is free is omega on the top. Everything else, so SQ is identified to SQ here, is identified to SQ here, QU is identified to QU here and QU there. So none of those are free, and the internal ones are also not free. So the only one that's free is omega. So so it's like a dunce set, but not quite. And this has this property that it has a unique free face, and it's also collapsible. It's collapsible because, as you can see, the optimal gradient vector field has just one critical simplex, S. What's also nice about this is that this particular triangulation of the modified dunce set has 39 simplices, and it is shown via some experiments in some other papers that any such complex that is collapsible and has a unique free face will have at least these many simplices. So in that sense, it's minimum. This is useful because this number 39 comes up in, or the number of critical, number of simplices in the complex comes up in the reduction. So the lower this number is, the better hardness result you get. It's kind of relevant. Yeah. Be improved. Yeah. But the point was that by experiment, I think Powell Pudlak showed that this is the minimum you can have. So anything that has fewer will not have this property. So now I'll describe the details of this reduction. So let's recall. So first we are looking at a way to transform the instances of acyclic subgraph to instances of Morse matching. So let's see how that can be done. So first, what you do is, to every edge in the graph. So you start with some graph G. Now this graph, remember, is oriented, means it has no parallel edges or loops, and it is degree 3, which means that in degree plus out degree is 3. So you start with any such graph, and we are trying to build a complex from which corresponds to this graph. So here this is a simple graph G, and this is the complex Kg that comes out of it. And the way this is done is that you start with a dunce set, you start with a disjoint union of dunce hats, one for each edge. So for this edge you have dunce hat, for AB you have dunce hat DAB, for BC you have dunce hat DBC, and for BD you have dunce hat DBD. So remember, for every edge you have one dunce hat, modified dunce hat, and the identifications you make, the rules of identifications, are per vertex. Okay. So for every vertex V in VG, so let's say you're looking at B here, you make identifications as indicated by colors. So the incoming edge AB, so you look at dunce hat DAB, and you choose, you have this special edge phi and psi, and these edges are identified to omega. So this psi is identified to omega of this, and phi is identified to omega of that. So, and then you also have rules when you have two incoming, one outgoing, one incoming, one outgoing, all three incoming, all three outgoing. But I'll not show that. It's kind of similar. You basically, the idea is that what you do is, to recall once again, you for every edge you have one dunce hat, and for every vertex V you have some rules, and the rules are based on how the in degree plus out degree. So for this example, we see how this is to be done. So you identify some of the internal edges of the incoming edge to the free faces of the outgoing edges.
So omega is not an edge in that modified transfer.
What do you mean?
Remove that edge.
No. Oh, sorry. Yeah, I think maybe this is bad notation. It's not removed. It's free, and I just wanted to show
You just want to highlight that
it's free. Yes, it is not removed. So it is still a simplicial complex.
that's
So
the only free.
yes, that's the idea. That's the only free one.
Even after your identification, you retain that one free edge.
So now it will not be free anymore.
Top omega.
So because now omega is same as psi, and now it will have 1, 2, and 3 cofaces incident on it.
But then the omega from DAB.
That one is free. The top one is free, but the ones here are not free. So that's the idea. So if vertex A has no incoming edges, then the edges that come out of A will have dunce which will have free faces. And if you have anything that's incoming, then then the edges that go out from that will have dunce that have free faces gone, meaning that they will be identified to something else.
Outgoing scenario, so that will have that omega edge identified and it will not remain free.
Yeah. If the outgoing edges also have some incoming edge, so the idea is that if you have some incoming edge and some outgoing edges, then then the internal faces of the incoming edges are identified to the free faces of the outgoing edges. So then the outgoing edges will not have dunce which are for every vertex you go and see, you make identifications. So this is shown only for one vertex, but let's say you have a big huge graph. First you start with a union of dunce one for each edge. Then you look at every vertex and start making identifications based on incoming and outgoing edges. And now let's say you have, so let's look at another example here to clarify the idea. So this also shows one more construction. So you start with this cycle, which is a graph, also oriented degree 3 graph. And so you have edge AB, and you have DAB, and you have BC. So you have DBC. So as you can see, the purple edge phi of that is identified to the incoming edge, the free face omega of DBC. And this edge is identified here, this is to there, and so on. So now as you can see, when there's a cycle for this, you have no free faces left in this complex. So everything is kind of blocked. So when you have a large complex and you have a lot of cycles, the idea is this that when you have cycle and so in some graph you have a lot of cycles, a lot of direct cycles. Then if you want to find the optimal number of cycles edges that you need to remove, this is hard. And if you were able to find a method, some magical way to for this complex, and if you were able to find some gradient vector field with minimum number of critical 2 simplices, then this would also give you a way to find very few edges to remove for the max acyclic subgraph problem. So this tells you that this cannot happen, and there's a formal way to do this, which we'll see. So the solution to solution construction goes like this. So what you do is you have a gradient vector field here, as shown in this figure on the right, and you want to construct an acyclic subgraph on this. And the rule for that is the following. So you look at the feedback arc set is the set of edges where the corresponding dunce hat has a critical 2 simplex. So if you look here, your dunce hat has 2 critical simplices. So this is a part of the feedback arc set, and that one has 1 critical 2 simplex. So this one is included, but the other ones don't have critical 2 simplices. So those 2 edges are not a part of the feedback arc set. So like I mentioned before, we are not just going from optimal to optimal. So this is suboptimal. for this complex, this gradient vector field is suboptimal. And also for this graph, this feedback arc set is also suboptimal. But you have to have a way to go from all solutions to all solutions. And there's a proposition which says that when you construct a set of edges in this way, like when your f is defined in the following way, then such a set of edges forms a feedback arc set for the graph G. Now, there are some properties of this reduction which helps you prove the hardness result, and I'm listing only the most interesting or elegant ones. One is that this complex Kg is homotopy equivalent to graph G. So in a way that you can like shrink this complex to the graph G. It has the same homotopy type. The other one is that if mu2 kg denotes the minimum number of critical 2 simplices for complex kg. So like you saw in the previous slide, the critical 2 simplices are what are relevant, not the other critical 1 simplices and 0 simplices. So if let mu2 kg be the minimum number of critical 2 simplices for kg, then mu2 kg is 0 if and only if G is acyclic. So you have no critical 2 simplices on kg if and only if your graph G is acyclic. And more generally, so this statement subsumes what's said here. Your mu2 kg is actually equal to the optimal value of min feedback arc set on graph G. So the minimum critical 2 simplices you will have on kg is equal to the minimum number of edges you need to remove from the graph to make it acyclic. So they have this correspondence. So based on these propositions and some other propositions, we now use these results to do what is called an L reduction, to perform what is called an L reduction. And this goes as follows. What you do is, I hope you remember, we went from graphs to simplicial complexes, so instances to instances, and we went from solutions to solutions, which were gradient vector fields, and we went to acyclic subgraphs from there. And the above reduction is an L reduction if and only if there exist constants C1 and C2 which satisfy the following properties. The optimal value of on Kg is less than or equal to some C1 times optimal value of G. So the optimal value of max Morse matching for Kg is less than or equal to some constant C1 times optimal value of max acyclic subgraph on graph G. And val is the objective value for a solution. So the objective value of a solution. So first property is, so you're basically, it's the reduction that you should do any reduction, and that such a reduction is an L reduction if two linear inequalities are satisfied. One, if the optimal is some constant less than or equal to some constant times the optimal of the original problem, and the difference between optimal and value of a solution is also proportional to optimal minus objective value of a solution for the other problem. So if they are related by two such constants C1 and C2, then such a reduction is L reduction. It's called L reduction because it's linear. They are like these are linear inequalities. In the first one relates the two optimas, and the second one relates the difference between optimal and objective. So optimal and objective of some solution, and this value and this value are correspond in the sense that solutions correspond to solutions. So when you have such a reduction, it's an L reduction, and this is what we show to establish the reduction. We show that this reduction that we did from acyclic subgraphs to complexes is an L reduction, and with this L reduction has two constants, 78.5, and once you have that, you now use what you already know about 3 O mass. 3 O mass is max acyclic subgraph restricted to degree 3 oriented graphs. So if it's NP hard to approximate 3 O mass to a factor, this is already known from Newman and Guruswamy. So So it's NP hard to approximate 3 mass to a factor better than 1 minus 1 over 126, and it's UGC hard to approximate 3 mass to a factor better than 1 minus 1 over 18. So UGC is some other conjecture about a unique games conjecture, exactly. So assuming that this conjecture is true, then you can attain stronger or better hardness results. It's not known either way whether this is true or false. So assuming so you have these two hardness results already known, and using the fact that the reduction that we just showed was an L reduction, we can prove the following about max Morse matching. You can show that max Morse matching is NP hard to approximate with a factor better than the one that's shown there. So this 39 is the number of simplices in the dunce set. So if you can see, this easily follows from the above. I mean, you have to show a calculation of why that happens, but it's not very difficult. So among the open problems, so what we haven't done is I have not shown the hardness proof for min Morse matching on two complex. In this paper, we only establish a hardness result for 3 or higher dimensional complexes. So hardness of min Morse matching for 2 complexes is open, and I'm working on Uli Bauer and I are working on that. So hopefully we'll have something soon. But right now it's open, and if you look at the gadget itself is a non-manifold complex. It's not, because you have your complex is not a manifold, so nothing is known about hardness of. In fact, it's not even known if it's NP hard. The finding the optimal is NP hard for Morse matching. I mean, it's believable. It would be a believable conjecture to say that it's NP hard, but it's not known. And of course, nothing is known about the hardness for manifolds. Another open problem would be to close the gap between approximability and. So this approximability result is in paper with Tala and Professor Natarajan, and this one is in approximability result that's established in this paper. So closing the gap would be another open problem. So there's a huge gap, as you can see. So yeah, that concludes my talk. Let me know if you have any questions.